A few videos ago, I did a video on emulating the ColecoVision system, but I didn't have emulation of the sound chip in that ColecoVision system at the time. So I've now added the emulation for the sound chip, which is the SN76489A, and I've put it in my ColecoVision emulator, and I'll demonstrate that now. And what I'll do in this video is I'll go through a couple of games, and I won't talk much during the games because I'll have this, hopefully have the sound up to a degree that it can be heard on my phone. I'm not sure if the phone blocks out some sounds. Hopefully it'll come through okay. And then after I've demonstrated a couple of games, I'll do a couple of levels of each game. I'll go through the theory of how you actually emulate a sound chip using C under Linux, and then I'll go through the source code as well at the end of the video. So the first game I shall select, I quite like Gyrus. So the sound, so on my Z80 processor that I've emulated, I haven't put the time-ins in for the undocumented instructions. So I'll put the undocumented instructions in, but not the time-ins. So I need to put those in. So it may not sound 100% right, but it should sound pretty good, hopefully. So next game I'll emulate is a Pac-Man, I think, because Pac-Man's quite a good one to do. And of course ColecoVision, you have to wait a little while before you can actually start a game. It just has a title screen for a few seconds. actually quite surprised how little source code it takes to emulate one of these sound chips. But I'll get to the source code after I go through this theory of how the actual emulation works. So on the actual emulator, I'm emulating the ColecoVision, and everything revolves around the Z80. So the Z80 takes control of the emulation from the start, and it will read the ROM cartridges, the bytes by byte from the ColecoVision, and it will execute those bytes in sequence as a program on the Z80 CPU. And after a while, it will come across an out opcode, which is an output to a port, and the port will be for the sound chip. Now it does output on other ports as well, because it uses outputs for things like the display driver, but in this case it will come across the ones for the sound drive and pass them on to the sound emulation, which I'll go through the source code of. And that sound emulation, it won't do anything with that straight away, without out command straight away. What it'll do is it'll build up a set of values to actually play on audio. It'll build up a few milliseconds of audio, and then it will pass that audio onto the Linux audio driver. In this case, I'm using the ALSA library under Linux, which is nice and easy to use. And when I go through the source code, you'll see how easy it is to use, and how you can probably use it for quite easily for other applications like synthesizers or things like that. So what happens on the emulation of this sound chip is I'll have an array of values which get recorded. So each output instruction, it will get a value. Now in the example I'm showing here, I'm using just 1 byte, so 8 bits, just to simplify the numbers, make the numbers smaller and easier to read. In my actual emulation, I'm using 16 bits, but you could use a higher number of bits as well, depending on how much definition you want to use and how much processing you want to actually commit to this emulation. So say I've got an array of values, of byte values called wave, and it records the first one at 0, and then the next one it gets at 120, 220, and the maximum value 255, and it comes back down, and it's recording a sine wave. And this is just an example. These values could be anything, so it could be a square wave, triangle wave, or any arbitrary kind of waveform. But just for this example, I'm just showing a sine wave because, again, it's nice and easy to understand. So it builds up not just one of these waves, but a series of waves which output a frequency to the audio. And it'll do that. It'll build that array up until it's got a few milliseconds of audio, and then, like I'm showing here, it passes it on to a buffer in the ALSA library. So it'll call a function in the ALSA library which will say add this data to your buffer, and so that buffer will build up, and then it's down to the ALSA library how that ALSA library then processes that. So we don't have to care how that processes it. If I was doing, hopefully, ultimately I'm going to be doing it on Pico, a microcontroller, in which case I'm going to be using DMA myself to output the data, but the data will still come into my own driver for the audio, and I'll probably have a buffer which I then just tell DMA to send to a speaker using PWM or something like that. But in this case, like I say, under Linux, I'm just sending it to the ALSA library. Don't have to care about it from then on. It will just stream that to a speaker then, and that's how the emulation in theory goes. So something which needs to be taken into consideration when emulating one of these sound devices. This particular sound device has 3 channels: channel A, channel B, and channel C for doing audio tones, and it has a noise channel in addition to that. But all of these channels, if you're playing something on 2 or more of the channels, it needs to be mixed together. And because when you mix things together, basically it's doing an addition, a basic arithmetic addition of the waves. So any individual channel can only be, as I've got effectively 4 channels, the 3 tone channels and a noise channel, any individual of those channels has to be maximum 1/4 of the overall volume of the output of the audio device. And I'll go through why that is here. So here I'm showing each of the channels playing at their maximum volume. So each individual channel as well on this device, say we take channel A, the volume on channel A can be set anything from 0 to 15. So anywhere in 16 steps of the audio level from silent to audio of maximum for this channel 15. I'm showing here them at their each channel at their maximum volume, but they could actually be at lower volumes than I'm showing here. But to demonstrate why they can only be a quarter of the total volume of the output of the audio, I'm just demonstrating the maximum volume for each channel here. If you look at this grey highlighted area, if you add up each of the channels, so 1 for a high or 0 for a low, each of the channels, so channel A is high, so 1, channel B is high, so that's 2, C is low, and the noise channel is low, so that's a value of 2. So if you look at the bottom where it's mixed, it consumes 2 blocks from the very bottom. But if you look at just before the grey highlight, on channel A it's high, B it's high, so that's 2, C it's high, that's 3, and the noise channel is high as well, so that's 4. So that's 4 blocks on the mixer. So that's why each has to be a quarter, at maximum a quarter of the output volume, because otherwise it would clip, it would be too much for the output amplifier, and you wouldn't get proper noise. And also if you look just after the grey highlighted area, channel A is 0, B is 0, C is 0, and the noise channel is 0, so you get 0 blocks on the output of the mixer. So you get, when it's mixed together, it forms this waveform that you see in the mixer. So each one of them is a regular tone of a fixed noise, fixed high and fixed low spacing, which are equal. The high and the low are equal. So each one's channel A is a tone, channel B is a tone, channel C is a tone, which is lower than the other tones, and the noise channel is just random output to create some noise. And that generates the output waveform that you see on the mixer. That gets sent to the ALSA library, which adds it to the buffer to be streamed out to the speaker. So this is the source code for the driver for the sound chip. And at the top I've just defined some waveform data. I've defined waveform data here, and I've made it constant data because when I actually come to put it on the Raspberry Pi Pico, I want it to reside in flash memory. Here you can see where I started out, and when I originally wrote the source code, I dynamically created an array of data to actually create the waveforms, and that would reside in RAM because it's just created dynamic on the fly, so it's going to be put in RAM. So I didn't want to do that, so I've kept the original source code here just in case I want to recreate some of these waveforms with different definitions or anything. It's always handy to have that. But what I'm actually using is these constant arrays of values, and they're 16-bit values. Now I've got a sine wave here. The actual chip itself only uses square waves, and that's the same with the chip that you find on things like Spectrum, where you use one of the AY3 chips, and uses square waves. But I took advantage of the fact that because I'm writing this driver myself, I thought it'd be good to be able to substitute any kind of waveform I wanted in to see how it sounded differently, depending on what kind of waveforms I'm using. So I've defined the sine wave here, and I've defined the square wave here, which is the one which is used by default, and the one which you would have heard in the demonstrations I played at the start of this video. And then I've defined the triangle waveform, sawtooth incrementing waveform, and a sawtooth decrementing waveform. So I've got some at the top of the source code, some static variables, just these are local global variables, so I can keep track of how the actual waveforms are being generated from one call to the next call. So when an output instruction hits the Z80 emulator and it calls this driver, next time an output instruction is sent, I still have the actual values which were set last time, so I can keep consistent waveforms being generated rather than being broken up because it forgets its status from one call to the next. And I keep the register values which the sound chip has in just an array of register values. Now some of those register values are 8 bits long and some of them are 16 bits long, but I've created it 16 bits long because that's the maximum value, and I can fit an 8-bit value into a 16-bit value, it doesn't matter. And I'm selecting sine wave as my default set of waveform data, but actually when you call the initialize function, you actually select what waveform data it is. So this is kind of arbitrary. This is just an initialization value for when it's compiled. So here's the initialization function, and like I say, you pass in the actual waveform type that you want to actually pass in, and you'll see when we get to the source code of the actual ColecoVision, I will be passing in a square waveform type. Then I create my own buffer locally for creating the few milliseconds of waveform that I'm going to pass to the Linux driver. So this is my buffer and not the Linux buffer. And before I start doing anything, I make sure that I've successfully managed to create a buffer for myself, and that I've got a valid waveform which I've selected, which will be selected from this type which is passed in. I open up the Linux ALSA driver, like I open up a file system. It just gives you a handle which you can use so that when you call it again, it knows which application is talking to it, and it can handle whatever you're sending it. Set up parameters for the ALSA driver. I'm telling it I'm using 16-bit values, and I'm telling it I'm going to send it interleaved stereo audio. So I'm going to send it left channel data, then right channel data, then left channel data, right channel data. Just one data value at a time, left and right. I set up a sample rate. Now I actually use an unusual sample rate. It's 88 kilohertz, which is twice as much as you might consider for high quality sound. But I find it gives a better quality sound because I think the speed at which the audio can be changed by this processor by sending output values to this driver, it reacts better to those, and I think that's probably why it gives it much better output. I've tried 44 kilohertz and it gives decent sound. I also originally was going to try like 22 kilohertz, but that's not so good. So you need at least 44 kilohertz, but actually 88 kilohertz is the sound which gives the best result. I tell it that the actual Linux sound driver not non-blocking, so that when I send it some information to play, it doesn't just play that and then only return once it's played that. It will take that information to play and it will turn control to me so I can get back to my emulator and continue running the emulation. So this is where I select the wave type that wants to be played. So if the application says give me a sine wave, then play the sine wave, or square wave, or triangle wave, and it's just interesting to mess around with that. Then I just call the reset of the emulation of this chip so that it starts from a consistent state, like it would if the CPU was reset. There's a terminate function which is called when ending emulation, and all that does is it tells the Linux sound driver to finish playing what it's playing, and then it tells the Linux sound driver to close down the device as far as this application is concerned. It's not going to use it anymore. And then my own buffer, which I use for audio, I tell it to free up that and give the memory back to the operating system. So this is what happens when the Z80 resets and tells the sound chip to reset as well. I check how many frames of audio the ALSA driver has available for me to give it data, and if it returns a negative value, then it means there's an error, and I tell the ALSA driver to recover sound, because I'm resetting and this could be happening sort of at any time, just in case it kicks up an error, or in case it had failed previously. I just give it an opportunity to recover, the ALSA driver to recover and start playing audio again. I clear the values that I'm recording for the sound chip registers. Just set them all to FF as the default value. And then I set my own channel counts, which keep track of where in the wave table each channel is pointing to make sure that I'm starting off from the beginning of the waveform data for when I start playing audio again. So the emulator itself for the audio only has two functions. This is the first of the functions, and that's where an output instruction is sent to the emulator of the audio chip, and an output instruction sets a register within the audio chip itself, and that's all the output instructions do, set registers, and then the audio chip then takes those values and creates sound from what they define as what sound needs to be created. So I'm storing, like I say, you can only send an 8-bit value at a time because the Z80 is an 8-bit CPU, and this chip operates on 8 bits as well. So when it gets a data byte, if it wants to store a 16-bit value in a register, it has to send 2 bytes. So that's why I'm having the register here, which is static, so that it remembers it between calls, so it can build up a 16-bit value if it requires for one of its registers. Now this particular chip itself only accepts output instructions, but rather than just assume it's going to be an output instruction, just in case the program in ROM for some reason tries to read from the chip, I explicitly say, okay, only if it's doing an output instruction will we set any of these registers. And so this is the top bit of the data byte which is sent from the output instruction. The top bit defines whether it's a high byte or a low byte of the register. So I store in the register data whether it's high byte or low byte, so I can build up the 16-bit value as required. And then I decide which register it's actually writing to. So in the actual register data, it will it will define which register number it's going to write to, and that's handled by this expression here. And then if it's saying it's setting the tone of channel A, then I set in my registers, in my 16-bit value for the tone of channel A, I build up from both the high byte and the low byte of the register value, shifting the values as required and masking them out as required to create its value, because the actual value itself isn't 16 bits, because here you can see 4 bits or three bits here define which register number you're writing to, and then there's the top bit as well, which defines whether it's a high byte or low byte. So we only get the bottom 4 bits, or we get the bottom 4 bits plus an 8-bit of the register 0, the first register value which is sent. So we get 12 bits to define the tone of each channel, and so that's what's being built up here, and it's getting set into the tone register. Then you can, if it requires you to set up the volume, so if you get an output instruction saying set the volume register, what it does is, if the value is 0F, so if the last value, so I haven't set it yet, what I'm doing is I'm checking the last value which was in the volume register, and so if the channel was turned off, which is the 0F value, then I set my waveform pointer to 0, because if it needs to be set back to 0, because if we're turning the channel on, we want to start the audio from a clean point of the waveform, otherwise it gives you clicks and funny sounds like that. Then I set the volume register to the 16-bit value. Sorry, the 16 is a 4-bit value. Maximum is from 0 to 15. The value is from 0 to 15, so 16 values in total. But I'm setting the volume register to whatever the value is of the 4-bit value. But when I come to use it in my actual application, I want kind of the inverse type value for volume. So I want it counting in the opposite direction, rather than from 0 to 15, from 15 to 0. So that's why I have 15 minus whatever's in the value. And I make that calculation here because I don't want to keep making that calculation every time I'm playing, because I'm going to be playing it a lot more times than the registers are being set. So I'm saving CPU time by setting that value here. If you set, it sets the tone register for channel B, and it does that in the same way as it does for channel A, and it does the same with the volume for channel B as well. It sets the same way as it would do for channel A as described above. Same with the channel C tone is set in exactly the same way as the two channels above, and the channel C volume is set in exactly the same way as the two channels above. So the noise channel, it has its own definition of bits of how the noise is to be played, and so all I do is just store that into the register so I can remember when I'm actually playing the noise, how it's supposed to be being played. And you can also set the volume for noise in the same way that you can set the volume for the other channels, and that's just the 4-bit value. And again, I change it so that it's a decrementing value rather than an incrementing value. Then the last function in the emulation of the audio for this chip is to actually play the audio. And so what that does is, for playing random noise, it needs to remember some values from last time of how random the random numbers. So in order to generate a random number, I don't actually call a function to generate a random number. I actually generate the random number myself in this within this function, because it's to save CPU time. Because again, if I'm calling into a function, that takes a lot of time, and if I'm just calling a random function, I might as well create a random number myself, which luckily turned out to be simple enough to do. So what I do is I generate a buffer size of audio in this each time this is called. So that few milliseconds of audio. So I've got channel A, B, and C set to certain tones, and the noise set to a certain tone if all those channels are turned on. So I just generate a sample of audio which is of those tones combined, mixed together, and then I can send that off to the audio card, and each time it's called, it will generate whatever's defined to be the audio in the registers for a few milliseconds, and send it to the audio each time. So here I'm saying if the channel is enabled for channel A, it checks to see, so there's an adjustment it does to make the pitch sound correct. So the sound that I'm playing may not be correct pitch because I'm not like an audio expert or anything, but I've done an adjustment because it needs to just be tweaked in order to make the pitch sound correct for the audio playing back. So once it's done that adjustment, if it's not pointing within the waveform table that's been defined for this channel, then it will reset that waveform table pointer back to the tone which is required for channel A, and it does that with all the channels. So channel B here, if it's enabled and it does the adjustment for the pitch, and we've come to the end of the waveform table, it'll reset the counter for the waveform back to whatever the tone is required for channel B, and same with channel C. Now here you see we've got a loop which goes round, in this case twice, so there's two output channels for the ulcer driver, left and right. So I need to generate left and right data alternately within the array which I'm actually going to send to the ulcer driver. So by default the value is going to be 0 because this is the start of where we mix the data together to generate the waveform output. So by default we start off from 0 because we're going to add the channels in to this value. So only if the channel is enabled, the actual mixed value which I'm building up here for the actual output, I'm looking up the value in the wave table which I'm going to use, and from the maximum size of the wave table the position I'm within the wavetable, and I'm going to offset here the frequency which I'm playing. So I'm going to step through the wavetable at the frequency I'm playing. So the greater it skips the values, the higher the frequency it's going to be. So this should automatically take it. So it's taking it from the register value which was set by the Z80 processor of the tone of channel A, and it's going to automatically generate the frequency I need. And then I'm logically ANDing here. This is 0xFF, so because my wavetable is 255 bytes long, I'm ensuring here I can never look outside of that wavetable by mistake, because I'm doing a calculation here which could have a bug in it, which would write or read outside the actual data of the wavetable. I don't want that to happen. This is just like a safety feature here. It shouldn't have any effect on the actual overall result, but to make sure I never read outside the wavetable, I'm making sure I mask that out, any values outside of the wavetable. And then I'm actually scaling the value I'm getting back from the wavetable by the volume I want to play on this channel. So all of that line automatically does everything I want to do for channel A, for playing back a particular value in a particular position of the wavetable. And the same happens for channel B. Only if channel B is turned on, then I mix within the last value, because I'm just adding to it the channel B value, whatever happens to be that it's using the same wavetable, but it's going to have a different position in the wavetable, and the rate at which it skips those values is going to be different for a different frequency. So this just builds up channel A, B and C to add the frequencies which are playing. If a channel's not enabled, then it won't add it, and it will only add the channel if it's enabled to the extent that the volume for that channel set is set to. So that's incredibly simple code if you think about it, actually, to generate a waveform for the audio. So there's not really that much to actually emulating the audio for one of these chips. And I've already written the AY3 chip emulation. In fact, this is a cut down version of that, and it generates noise slightly differently, but they're basically the same code to emulate both this chip and the AY3 chip. And this is where it does the noise for the noise channel, and only if the noise is enabled, what it does is it steps through a random size mark and a random size space for the waveform, and it generates random ones each time it does a mark space. It generates new random length for the mark space, so that generates a noise. So for the default noise space, it decides if it's white noise, it adds a certain amount of frequency to it, and then generally for noise it has an additional frequency which is added. So this is kind of the formula which is generating the basic noise for the noise, and this is just what I've come up with. So this may change at some point because the noise may not be exactly right. I haven't really compared it with I haven't got a real system, but I do have a real chip, and at some point I might play back noise on the real chip and get this a bit more accurate, because it's probably not that accurate for generating noise. And then because on the noise you can actually associate the tone in channel C, and you can associate that to the noise channel itself. So I'm adding the tone of the channel C to the noise if it's configured to do so in the noise configuration. And then by default I'm setting the noise and mark and space to the same value. At this point I'm adding pos buffer. Now pos buffer is nothing to do with the noise, but because each time this function is being called, pos buffer is going to be pretty random in itself. So I'm adding an extra bit of randomization just by adding this value in, because it's a constantly incrementing value. And this is where the randomness really happens, is you do an exclusive OR and you shift the value itself. So this is it's the same value, but I'm shifting it by 9 bits across, and that generates a pretty random kind of a value. Then this noise space value, I'm saying, is the space that the random value that we calculated there, and it only really wants to be the bottom 2 bits, and then I'm multiplying it by the noise space value, which was calculated up here, and putting it back into itself. I'm doing the same with the mark as well. I'm adding this random pos buffer. I'm shifting the mark around as well, but I'm keeping these two values, mark and space, separately, so they should generate different mark and space ratios. So it should generate a very random noise kind of sound. And again, I'm only looking at the bottom couple of bits and multiplied by the random value which I had up here, and that generates me the mark and space values which count down. So here I'm counting down the mark value if the mark value has a value. So if I'm still counting the value, then I decrement it by 1, and I set this is where I mix the mark value of the noise into the mixed value of the other channels, and again I'm scaling it by the volume which is set for the noise channel. And if I've counted the noise value down to the mark value for the noise down to 0, then this is where I add the space value and add the volume for the space, and then it decrements the space value up here until it gets down to 0. Then it calculates another mark and space for the noise up there. A bit convoluted the way I'm explaining it, but that's the general idea. And so that's mixed then, but all of the channels A, B and C and the noise into one value, which I can into one array of values. So I filled up my buffer because I'm going around loops of adding both channels and filling up my buffer, and I filled up my buffer with the frequencies set in that channel A, B and C, and the noise, and only if they're turned on. And here I'm telling the Ulsa sound driver on Linux to actually add what I've generated in my buffer to the Ulsa buffer, which is streaming out to the audio. I've got to do that at a rate where the Ulsa buffer doesn't run out of stuff, otherwise you'll hear breaking of the audio and stuff. So this has to be done at a reasonably consistent rate as well. And if it returns an error, so if it returns a value less than 0, then I tell the Ulsa driver to recover the audio, and that is the emulation of the sound chip. So this is the source code for emulating the ColecoVision. So at the top of the file, just like in the other emulations which I've done for other computers, you've got some global variables which are for the emulator. So for the CPU and the configuration. I've got the entry point for when I'm on Linux, which is a standard C entry point, and I've got the entry point for when I'm building the code for microcontrollers. So I set up the configuration, default configuration for this emulation from my configuration file, and I initialize the display, and it takes the configuration, the values from the configuration file for the X and Y of the display. I initialize the Z80 CPU. I initialize the audio chip, and I'm telling it to use a square wave here. So, which is what the audio chip uses in the actual in its physical reality. And I'm initializing the display chip here because it has a display chip rather than having its own hardware to do the display. Loading the ROM file for the ColecoVision, which is the default system ROM file. Just got a note here of the memory map for the ColecoVision. And I'm protecting an area of memory so that the ColecoVision doesn't try and write to it like it's RAM. So this is reserved for being ROM, and I'm unprotecting only the RAM area. So there's only about 2K of RAM or something like that within the ColecoVision. And then I just got an area where I can, on the command line, load up a cartridge if I want to, but I don't actually do that. I create all the callbacks for the emulation. So the clock callback, which is where the ColecoVision hardware is mostly emulated. CPU reset, so that I can do any custom resets for this particular hardware. So I'll do the things like the sound chip in there. And I've got a callback for setting the keypad. So on the ColecoVision, you've got a controller which has a keypad and a joystick, but only one of those is active at any one time. So this callback activates the keypad, and this callback activates the joystick. And I've got the callbacks for the display driver chip, and those callbacks go directly into the display driver hardware. So I don't have any code in here which actually handles the callbacks themselves. It's all part of the driver. And I set up callbacks for the controllers and for the sound chip. And I've also got alternate callbacks for the exactly same hardware, because there's 2 ports. So 99% of the games use this default port for the sound driver and the controllers, but there's a handful of games which use this alternate port number for some reason. Make sure the display is initialized and blank, and I start the execution of the emulation of the ColecoVision there. Then if it comes out of there, that means it's closing down the emulation. So I terminate the display driver, terminate the audio driver, terminate the Z80 CPU, and shut the display window. So this is the reset callback. So whenever the Z80 is reset, the Z80 will call back this function, and I tell it to reset the sound chip and reset the display chip. This is the callback for selecting the keypad, and so I just set a flag to remember that the keypad is selected, so later in the emulation source code below I know whether the keypad or the joystick is selected. And this is for setting the joystick, this callback, and I just reset the flag which says it's no longer having the keypad active, so the joystick will be active. So this is the controller 2, and I've also got the SN sound chip callback here because it's part of the same port as we're doing the controller 2. If it wasn't part of the same, if the sound chip was on its own port, I could have not had any source code here. I could have sent the callback straight to the hardware driver, but because I've got to capture the controller information, it means I have to do like a thing here. So on the port output, what I'm doing is calling what I would have normally called straight from the callback itself, and not needed stuff to be in this function. But that's the output. So it only does an output to the sound chip audio, because the sound chip audio can't be read there. But when it's reading on that port, it's reading from the controller 2, and it does a read of the keyboard on whatever device I'm using, which in this case will be Linux, and then it converts that keypad, the keys read from the Linux keyboard, into keystrokes which the ColecoVision would understand, so into key scan codes, and it returns whatever key scan code has been pressed. Or if the joystick was selected, then it will do the same, but it will look up whatever joystick button has been pressed. And so that was for controller 2, and this is a callback for controller 1, doing exactly the same thing. So the code in here is the same. It reads the keyboard off of Linux, and then if the keyboard is selected, it does a lookup for the scan code for the keypad, but if not, then the joystick must be selected, and so therefore it will do a lookup of the scan code for the joystick. And this is the main part of the emulation for the ColecoVision. And so this gets called back for every clock cycle of the CPU, and every period of time, which is defined, this constant here is defined within the sound chip include file, and this tells me how many times I need to call the play function on the sound chip. So this will generate one of those buffers of sound and send it to the also driver. So that repeatedly happens here, time after time, every time a certain period goes past. And then we come back into handling the display chip. And so every period of time it generates a non-maskable interrupt. So the sound chip on the ColecoVision, when it gets a vertical sync signal, it will generate to the CPU a non-maskable interrupt. Now on the MSX system it's different. It actually generates a maskable interrupt. So depending on what systems you're using, the sound chip might, the visual chip, the display chip might generate a non-maskable interrupt or a maskable interrupt, but on the ColecoVision they decided to use non-maskable interrupt, and that happens every vertical scan period, so that's every 50 Hertz. And then actually when I'm doing an update of display, I'm doing it here, and I'm setting the period here for the non-maskable interrupt. So here, this frame period does a 50 Hertz thing, but this NMI period means that a period after the display has been updated, it will then send the non-maskable interrupt to the CPU. And the reason for that is that certain games time when they're going to update the display, and so I want the ColecoVision to update the display, and then for me to update the display to actually display that data at the right period when the vertical sync should come in. So that's where this timing is going on, because that's the vertical sync period. So that will tell the CPU to actually generate the non-maskable interrupt for the video chip when it's required. Here I just do a scan of the Linux keyboard, and this is just so that I can have a break key when I'm debugging this emulation. So it's not for the actual emulation itself, it's for debugging. And here's where, if it's been flagged, if my emulator is flagged to say insert a cartridge, it will actually load the cartridge here for the ColecoVision. So it asks the user what cartridge you want to insert. They select it from the file selection menu, and then if they actually selected one, then it will reset the Z80 CPU and play that game. If they haven't selected one, it will just continue as it was before. And this is where I'd actually do the update of the display, so that occurs 50 times a second.